Normal cell division requires regulated flexibility. Mutations that alter this flexibility can cause cell division failure, which can lead to multinucleated cells, aneuploidy or an abnormal number of chromosomes, and cancer, as well as entosis, metastasis, and a greater ability to evade immune cell attacks. The protein mechanisms that drive these behaviors are being researched in the model organism Dictyostelium discoideum, an amoeba. When mechanical stress is exerted on a cell cortex, it is able to respond and become more rigid when cross-linking and motor proteins sense this force. The cortex is filled with polymerizing actin. Cortexylin-1, bound to these actin filaments, experiences force, helping it to accumulate further at the cortex, as well as anchor the cortex to the membrane. Filamin responds to shear deformation, which activates its catch bond, and cooperatively binds. And alpha-actinin responds similarly to stretching or dilation deformation. Hexameric monomers of non-muscle myosin II, or NM2, form dimers, which assemble into bipolar thick filaments, their functional unit in the cortex. Tension can freeze NM2 motorheads in their strongly bound or isometric state. Both strongly bound NM2s and catch bonds drive the accumulation of more of these proteins to share this force and make the cortex more rigid. For these proteins to act efficiently, they are pre-assembled in variously sized, nearby condensates called contractility kits, or CK. These condensates are stabilized by proteins such as discoidin-1. CKs exist within a spectrum of mechanoresponsive to non-mechanoresponsive states that are calibrated by scaffold proteins called IQ gaps, which competitively bind a cortexylin-1 to regulate CK activity. A single or a pair of IQ gap 1s can bind, one of each, or a lone IQ gap 2. IQ gap 2 confers mechanical sensitivity. IQ gap 1 inhibits this sensitivity. There is always a gradient of both. Whichever is present in greater number drives overall behavior. During mechanical stress, mechanoresponsive kits disassemble and associate with the cytoskeleton at the cortex when needed. When the stress subsides, the proteins begin to dissociate from the cortex and reassemble back to their contractility kit states. This research has led to the discovery that the compound 4-HAP causes the accumulation of NM2s from contractility kits into the cortex, thereby making cancer cells more rigid and preventing metastasis and their other characteristic behaviors from occurring.